So hello, this is lecture 1 of group theory for IIT Jen. Here we'll discuss the all the topics, basis topic related to group theories and some short tricks for doing the problems in this lecture. So our first topic is binary composition. So binary composition is what? Let S be a non-empty set. A binary composition or not on S is nothing but a mapping from not S process to S defined by not A comma B is equals to A compose B. If A belongs to S and B belongs to S, then A compose B belongs to S. This is our main topic of binary composition. Binary composition is nothing but a mapping where we take two elements from a set S, and then the relation will then the mapping of those two elements will create an image on the same set. For example, it will be more clear by when I will give an example. So usual addition plus is binary composition for the set of rational but not a binary composition for the set of rational numbers. If I want to be more precise, 2 and 3 are rational numbers. If we simply add them, it will give 5, which is also belongs to set Q, which is set Q of set of rational numbers. But 2 minus root 2 is a irrational number and 2 plus root 2 is a irrational number. But their sum is 2 minus root 2 plus root 2 is equals to 4 is not a irrational number. So 4 does not belong to the set of all irrational numbers. So the binary operation on this set is binary operation addition is not defined on the set R minus Q. Next topic is our semigroup. An algebraic structure G compose where G is a non-empty set and this is a binary operation on G is said to be a semigroup if this is a groupoid, means it follows the closure property, and this follows the this algebraic structure follows the associative property, i.e. the This algebraic structure follows this two property. For all a comma b belongs to G implies A compose B belongs to G, and for all a comma b comma C belongs to G, A compose B compose C equals to A compose B bracket compose C. Next, definition of a monoid. If an algebraic structure G naught satisfies these properties, that satisfies one closure property, i.e. A comma B belongs to G implies A compose B belongs to G. The associative property, A comma B comma C belong implies A compose B. Here naught is the binary operation and G is the set, non-empty set. And there exists the identity element, i.e. there exists E belongs to G such that A compose E equals to E compose A equals to F for all A belongs to G. If these three properties are satisfied in algebraic structure, then it is called a monoid. Next, definition of group. If G is a non-empty set and naught is a defined binary operation, then 1. If the closure property is satisfied, 2. Associative property is satisfied, 3. Identity property is satisfied, 4. And for all A belongs to G, there exists an element, say a dash unique element, A dash such that A compose A dash is equals to A dash compose A equals to E, where E is the identity element. Every element A for all A belongs to G, there exists a unique element, a unique inverse A dash. So the existence of a unique inverse. If these four properties are satisfied, then the algebraic structure G naught is called a group. Next, some examples of groups are the set of all integers forms a group under addition, but this does not form a group under multiplication. It's a group, but this is not a group. Because why? Because for the element, say element 2 belongs to Z, its inverse will, and its identity element is clearly 1 under operation multiplication. But there does not exist any element x such that 2x equals to x into 2 is equals to 1. Basically, the value of the x will be what equals to 1 by 2. That does not belongs to Z. So this is not a group. Next, similarly, the set of all rational numbers forms a group under addition, but set not it's not a group. It forms a group under addition, but it doesn't form a group under multiplication, because the inverse of the element 0 does not belong to Q. But if we consider set Q star such that Q minus the element 0, then this set under operation multiplication will form a group. Similarly, the set of all if a set R star is equals to R minus 0, then this set of this set under operation multiplication will also form a group. Again, for some n positive integer n, Zn equals to 0, 1, 2, 3, n minus 1. The set is like this. Are all the this is basically all the remainders when any number is divided by n. This also forms a group under operation addition, under binary operation addition. The set of all matrices also all matrices of order n cross n or n cross n also forms a group under binary operation addition. The set 1 omega square, i.e. the complex roots of 1, also forms a group under multiplication. This is what the cube root of a set of cube roots unity. Thus, in the quaternion group, which is like this, this also forms a group. This group is named quaternion group. We'll study about this later. And this is called K4. A set like this, A, B, A, B. This is called Planck's 4 group. We'll also learn about it later. For now, just let this set forms a group, and the relation that this set holds as E is the identity element, and A square equals to B square equals to E, and AB square is also equals to. These relations hold in this set, then this set will be called a Planck's 4 group. Next, there are some definitions. First comes the order of a group. Order of a group is nothing but the number of elements in a group. So, the order of a group is nothing but the number of elements in a. So we know Zn is a finite group for some n. So order of, and it contains n elements. So order of Zn will be what? N. But set of all integers is an infinite set. So, and this follows a group under addition. So order of this group will be what? There are infinite elements. So order of Z will be infinite. Next, order of an element in a group. Now we'll tell what is the order of a group element. Let A belongs to G be any arbitrary element of the group, and E be the identity element of the group G. Now we'll have a positive number. We'll have a positive number R such that e to the power R is equals to E. We are composing that binary operation R. We are doing that binary operation R times on E such that e to the power R is E, and this is not only a positive number. This is the least positive number such that e to the power R is equals to E. Because if we check, we'll check later. We can say e to the power 2R will also becomes to E, because this is what equals to e to the power 2R means what? E to the power R composite to the power R equals to E composite E equals to G. Now if there doesn't exist such a least positive integer for any element A belongs to G, then we say order of A is infinite. So from there we can say the group is also a group of infinite order. Now some important results on order of an element. Number 1, if G is a finite group of G is a finite group, then order of any element of G divides the order of G. Say G is a finite group of order say 20, the order of any element of the groups. So A belongs to some arbitrary element of the G. Order of A will divide the order of G. Basically, if we want to write this mathematically, this will be shown like this: order of G divides order of A. Next thing is the order of the conjugates elements are same, i.e. for any two elements A comma x belongs to G, order of A is equals to order of x inverse A x. The next thing is if A belongs to G and order of A is finite, i.e. there exists in positive integer in such that e to the power m is equals to e, where e is the identity, implies or then implies if for any other integer, say r, e to the power r, say r, any positive integer which is greater than n, or positive integer, sorry, I can say this greater than equal to be more precise, positive integer, and there exists a positive integer r which is greater than or equal to n, such that e to the power r equals to n. So we can say a r is m divides r. And now next point, for any two elements a comma b belongs to G, order of AB equals to order of BA. Next point, let a comma b be two elements of finite order of a group G such that order of A and order of B are 2 primes. Then if AB equals to BA, then we can have order of AB equals to order of A into order of B. Now there are more 3 properties left. I've studied all these properties before in the lectures of group theory which I have taken. The 6th property, order of a to the power k equals to order of A divided by order of A divided by GCD of order of A and K, where K belongs to N and order of GCD of order of A K. Yes, I have already done. This is the GCD of K and order of A. Now in problem point number 7, this is an important point which I haven't discussed till now. Everything I have discussed, the properties for short problems. I have done these properties related proofs in the lectures I have taken for group theories. You can go and check them out. Now the 7th property, I didn't remember of doing this before, so let's just try to remember this. Later I will explain how this proof of this property. So just see, order of the property says order of G is if the order of G is 2n, where n is odd, there exists x belongs to G such that there will belong, if order of G is 2n where n is odd, then there will exist an x belongs to the group G such that order of x equals to 2. So if there is a group of order 6, I go into 3, there will exist an element such that of order 2. You can take example of S3 for this problem and check it out. I forgot to remember, S is the group symmetric group. Problem number 8. The property number 8. This I have also drawn for this property. The required book I have already done before. So the property self says if B is a prime and B is divided by order of the group G, then there exists an X belongs to G such that this is order of X equals to P. So till now what I have taught will become the group theory for IDGEN lecture 1 part 1. I will take another lecture 1 part 2 for the rest of the things, because otherwise the lecture will be too much long. So thank you for watching. Please like, share and subscribe. Goodbye.